I would like to introduce the first keynote speaker, Eva Miranda. So I will make a short introduction. So Eva is full professor in geometry and topology at University Politecnica of Catalonia on CRM Barcelona, and currently Friedrich Wilhelm Bessel visiting professor at Mathematische Institut der Universität zu Köln. She has a PhD on symplectic linearization of singular Lagrangian foliation in 2003. She was research affiliated to Observatoire de Paris since 2018 because she was have a share of excellence of Fondation Sciences Mathématiques de Paris in 2017 at Observatoire de Paris. She has awarded by many prizes. The last one is the London Mathematical Society RD Lecturer 2023. And also many books, and the last one is Action Angle Coordinates on Kant Theory for Singular Symplectic Foliation. And so I know I give the floor to Eva for his talk on From Alan Turing to Contact Geometry toward a Fluid Computer.
Thank you very much for the invitation to speak in this conference. It's a pleasure to be here, and it's a pleasure to talk about fluid computers in front of the water. So it's a honor for me to speak in this conference, especially because this is dedicated to Professor Lieberman. I had the pleasure to meet her, and I had the pleasure to get her questions in her seminar. This is a long time ago, when I was exactly finishing my PhD. So it was a very important person in my career, and I think in the career of many female mathematicians. And there is a connection also with my talk today, because there's going to be some contact geometry in my talk. I'm going to use contact geometry to construct a fluid computer. How is this possible? So I'll have to introduce some elements from geometry. And Paulette had been working on the problem of foliations on these contact manifolds, and especially Legendre foliations, which would be the equivalent to the Lagrangian case in the for symplectic manifolds. And so we are in Saint-Malo, and we see here the force. So we learned today that in Friday you have to pay attention, because maybe you are going to see these waves on Friday, right? So now I'm going to ask, it's a bit early in the morning maybe to ask this question, but let me ask, this is more a question that you would ask after a beer the first day, is what would happen if we throw 29,000 rubber ducks to the ocean here in Saint-Malo, precisely when there are, on Friday. Maybe we should try to do this. Why would you like to do this? This is not very good for nature, but indeed this happened in 92, accidentally, because there was a carrier called the Ever Laurel, which departed from Hong Kong and had to bring a lot of things, including 29,000 rubber ducks to Tacoma. And the carrier lost the cargo during a storm, okay? And then what happened is that, well, these were lost accidentally, and as you will see here, wait, I made an error. As you will see, where is the pointer? That's the pointer. As you will see here, all these, since they left, they were doing very strange paths, okay? Indeed, they were lost, all these 29,000 rubber ducks, they were lost in January, and it was only in November that 10 rubber ducks appeared in Alaska, in Sitka. In July 2007, indeed there was, in the news, in the British news, most of them were waiting, all the British people were waiting for them to show up in Britain, but apparently only one rubber duck showed up, and it showed up in Scotland. This could have many interpretations, but I leave it there. And indeed, they are famous. The trip of these 29,000 rubber ducks has inspired literature. You see there are books like Moby Dick, And they have been an inspiration. And today, they give me a good excuse to talk about the fluid computer. So what did we learn from these 29,000 rubber ducks? There is some science besides the nice thing about having the book called The Moby Duck. There was a guy called Curtis Evans Mayer who had been always passionate about the ocean, even though he was not a scientist. And he was studying the currents of the ocean by tracking the movement of flotsam. And indeed, he had been using a simulator called Oscures, which had been developed by an oceanographer, Jim Graham, and together they had been working on tracking all kinds of flotsam. They had been, for instance, one of the experiments they did is to throw a big amount of messages inside a bottle. Some of us here in this room have seen these horrible movies where we have to declare love to somebody, and you say, okay, what do? I put a message inside a bottle and I throw it to the sea. But this is a bad idea, because only 2%, sorry, my bad here, let me go back. Only 2% of the messages in a bottle are recovered, and of course, only 1% of the proposals are accepted with a yes. But one of the experiments that they did is to throw a big number of these bottles, and this is how they recovered these. This is why they believe these numbers were correct, because the messages they put is not a love message, but it was something saying this counts as $50. If you tell us that you got this bottle, we give you $50. And okay, this is maybe much more concrete than a love declaration. So so this is more or less correct. So only 2% of the messages that you throw on a bottle are recovered. So corollary, please don't use WhatsApp or this kind of modern methods. So all this story of the ducks saved me as an excuse to talk about complexity of the water, okay, and to talk about complexity, the relation between computational complexity and complexity of fluids. We've seen it here, we will see it here on Friday with the Grand Marée, and we've seen it in volcanoes all around, and we've seen it with tsunamis, and so there is some kind of complexity in the behavior of fluids. Can we say more concrete things about this complexity? So the question is, are fluids complicated enough to perform computations? And that's a question that has been in the air ever since Roger Penrose. This was explicitly asked by Chris Moore here, and very recently, in 2009, this question was resurrected by Terence Tao, because Terence Tao wanted to find a counterexample to a famous conjecture. I'll talk about this later on. And if we start thinking if fluids are complicated enough to make computations, let's take one of the first models of computers. Okay? Can fluids simulate any Turing machine? Okay? So indeed, this looks almost a question in science fiction. I was giving a talk in Madrid about this 1 year ago, and then somebody in the audience came to me and said, I read a science fiction book about what you are telling me. I said, really? Yeah. And then I looked at it, and it's the book of Solaris, which then became a famous film. Okay? And in the book of Solaris, we could read, this is a book by Stanislav Lem, and presents the idea of having a sea that can think. Okay? So we can read this in the book. For some time, there was a notion to the effect that the thinking ocean of Solaris was a gigantic brain, well developed, several million years in advance of our own civilization. Of course, this is science fiction. And a sort of cosmic yogi, a sage, a symbol of omniscience. So in a way, what I want to explain today is that we can, in a way, fulfill the dream of Stanislav Lem to really prove the existence of this thinking sea. And thinking sea for us is going to be that we can associate a Turing machine to the movement of the fluids. Okay? And still, this will not give us the counterexample that Terence Tao was after for one of the conjectures that I'll talk about later on. But, well, still it's an interesting thing to think of. We should maybe ask the experts, can we find a Turing machine? So if we could now put together in the same room Alan Turing and Roger Penrose, and this is something that we can do thanks to Midjourney. After several tries, you try several prompts, and you get, after several tries, maybe more than 20, I will not confess, you get a decent picture of Penrose talking to Alan Turing. And Alan Turing, of course, he said, machines take me by surprise with great frequency. And we know that Roger Penrose, there are completely deterministic universe models that are impossible to simulate computationally. So Roger Penrose has been studying in a scientific and also philosophical way the limits of computation. So can nature be reproduced as a computer? We've read in Nature just a couple of weeks ago if nature can simulate a quantum computer. Okay, so I'm going to talk about these things. So talking about the limits of computation and talking about important PhD thesis, that's the PhD thesis of Alan Turing. One of the problems at the beginning of last century, which was very important, was to know were the problems of decision. Problems of decision were problems that admitted a yes or no answer. And one of these problems is the halting problem, which is the problem of determining from a description of an arbitrary computer whether this program with any arbitrary input will stop at a certain moment or will keep on going forever. So in a way, is to ask if there is a supercomputer that can tell us if any other computer will stop or not. And this is a problem in logic. And in 1936, Alan Turing proved that a general algorithm to solve the halting problem for all possible program input pairs cannot exist. So he proved that the halting problem is undecidable. Okay? And now you're going to ask me, you are talking here about DAGs, you are talking about quantum computers, now you talk about the halting problem, you're talking about love messages that don't reach the aim of the love messages, so what is this talk about? So what does Turing have to do with the rubber ducks? Well, a summary of what I've been talking about. The method of scores used by Ingraham and Evans-Mayer could not localize all the lost rubber ducks. Only 2% of the messages in bottles are recovered. So the question is, what if finding the rubber ducks is an undecidable problem? So why it would be undecidable? It would be undecidable if we can associate a Turing machine or a supercomputer to the movement of these rubber ducks. Okay? So the question that I want to answer is, can we associate a Turing machine or supercomputer to the trajectories of the rubber ducks? Why? Because it looks from this experiment of the 29,000 rubber ducks that there could be ducks anywhere. Maybe these ducks that they were waiting in Brittany for a long time, and only one of them showed up in Scotland. Maybe it could be here in Saint-Malo. Oh, look, I have one here. Yeah, it looks like this was supposed to go to Great Britain. I will leave it there. Watch me. Okay, good. So let's work. Let's start talking about chaos. So the notion of chaos is going to be useful to construct this fluid computer. So I'm going to introduce chaos in the most basic possible way. And a good definition was given by Lawrence. So chaos when the present determines the future, but the approximate present does not approximately determine the future. That's a good description of what chaos is. And show me with a simulation. This would be the simulation. We take the initial conditions, which are very close, and when the system evolves, these conditions become very far away. By the way, this simulation and other simulations that will appear in this talk are due to Robert Ghrist, so I'm deeply thankful for him to let me use this in my presentations. So here we see that after a while, the three balls come far away, okay? So very close initial conditions become very far away. So that's a notion of chaos. Today I want to introduce another notion of chaos. Well, just to mention that the notion of chaos was developed by, well, usually we say that it's developed by Lawrence, but I want to put pictures of women in my talk. And indeed, it's not by coincidence that it was Fetter and Hamilton who contributed, indeed, to the computations that allow to prove chaos. And let me look at the Cantor set. And I want to look at the Cantor set because it will give me, you see, what I do is to take an interval, I divide it by 3, and I drop the middle part, and I do this by iterations, okay? And what remains up there is the Cantor set, okay? So now I'm going to use the Cantor set to construct a new notion of chaos. And indeed, this was not my idea. This is an idea by Chris Moore. Chris Moore did this in his thesis, in his PhD thesis. So attention, PhD students here. You saw what Turing did in his thesis and what Moore did in his thesis. Moore did something in his thesis that was in the news. This doesn't happen very often. And we see in the news, mathematician discovers a more complex form of chaos. Wow. Everyone would like to see people talking about their PhD thesis like that in the news, right? This doesn't happen often. What did Chris Moore did? What Chris Moore did was to work with the Cantor set that I just described, but in a more complicated manner. He considered the square Cantor set, okay? So, well, this would be the three-dimensional, but we just need the two-dimensional. I put the three-dimensional because it's cute, right? But what he did was to consider mappings between two square Cantor sets, okay? And to these mappings, he could associate a Turing machine. This, because of the halting problem, coined this new form of chaos, which is the logical chaos, which is the fact that if we can associate a Turing machine to a dynamical system, and here the dynamical system is the product of two Cantor sets, okay, then because the halting problem is undecidable, okay, maybe we have a logical abstraction to know where a particle of your dynamical system will be. And this abstraction doesn't have to do with classical chaos, where the problem of determining where a particle will be depends on our lack of ability to measure these initial conditions. Here, it's a logical abstraction, why we cannot find these particles. And indeed, what he did, indeed, I'm talking about dynamical system, and what is a dynamical system? A mapping can be a dynamical system. So indeed, Moore, what he did was to generalize a classical notion in dynamical system, which is shifts, to what he called generalized shifts. And then he proved that any generalized shift is a mapping between two square Cantor sets, okay? So by doing so, he was able to simulate any Turing machine. In a while, you'll see how we can relate a Turing machine, which I didn't define yet, with the square Cantor set, okay? What is a Turing machine? We all have this maybe naive idea of Turing machines like a very long tape, okay? So I want you to think of a Turing machine like a printer. It's a printer that prints states on a very long tape, okay? And in this long tape here I have 0 and 1s, and I have elements of an alphabet, okay? So a Turing machine is just a printer of states on a long tape. And it's very important to know that when it reaches the halting state, then the whole process of printing stops. So the Turing machine stops. Indeed, here we have a formal definition. I can think of a Turing machine as this, sorry. I can think of this Turing machine as this collection of states where there are two very important states, the initial state and the halting state, the alphabet, okay? And I need a transition function which tells me how this printer works. So the transition function is just the user's guide of this printer. So if the current state is the Q halt, then we stop the algorithm. Otherwise, this transition function is going to tell me how to go from one state to the other, from one tape to the other, and this epsilon, which is either -1, 0, or 1, tells me if the tape moves to the left or to the right, okay? And if you want, the printer moves the other way around. So here we have an example, okay? So in this example, we start, well, that will be the example. Here we are printing the state Q on 0, and now we change, okay, the transition function tells me that we change Q to Q prime, and we print to 1, and we move, and we have this +1. +1, it means that we shift the tape to the left. It may look a bit artificial because +1 makes me think I'm advancing. But when I move the tape to the left, the printer moves to the right, so that's okay. Okay? So here we have this, let me see if now I'm able to do this. Go back, go forward. So we see exactly this printer is following these instructions up there. So we see exactly how it works, and the printer advances to the right. Okay, so that's a Turing machine. Oh wait, maybe you don't like this definition of Turing machine. I'm going to give you another one. Because let's talk about Conway's game. Conway's game is a boring game, 0 players game. You just have some instructions, and the system evolves. It's a system of survival of cells following some simple rules. And the rules are if the cells are surrounded by other living cells, etc. This gives me instructions of survival. So here we can see how this Conway game is playing on a torus. I can play it anywhere. Indeed, it was von Neumann who proved that every Turing machine has a cellular automaton associated to it, and the Conway game is a cellular automaton. So if we don't like the image of the tape, think of this example. You have like different models of Turing machines. So I told you I was going to explain you what is the relation between the square Cantor set and the Turing machine. And the relation is very simple. Here we have the Turing machine, okay? I'm here on the initial state. So what we do is here we have the elements of the alphabet. Here we take 0 and 1, okay? And we put some of them are going to be to the left, and some of them are going to be to the right. I collect the ones on the left here, and here the ones on the right, okay? And I take these guys as exponents of the ternary expansion of some 2 elements, okay? These 2 elements, because the coefficients are going to be 0 and 1, are going to lay x and y are going to be on the Cantor set. And if I make a picture of this x and y as 2 coordinates, then this picture of the Turing machine at a certain time is going to give me a point on the square Cantor set. Is that understood? And that's exactly the key point. So I can think of square Cantor sets as at a certain moment, so each point of the square Cantor set gives me exactly a picture of the Turing machine at a certain moment. And when this Turing machine is advancing, this red point here is jumping at different points on the square Cantor set. And the way this point is jumping, I can think that's a mapping between 2 squares Cantor sets. And that's exactly the idea of Ghrist-Moore. So this is the way we can associate a Turing machine to a mapping between 2 square Cantor sets. And indeed, that's exactly the brilliant idea of Ghrist-Moore, and that's the key point. Indeed, Ghrist-Moore did more and was able to see that this mapping can be piecewise linear. But I'm not going to enter into details. I'm going to skip these details. And now I'm going to talk, goodbye duck. I'm going to talk about this idea of associating dynamical system to Turing machines. What I did right now is an example, okay? But I want to talk about associations, because I could do associations that are not good. I want to talk about good associations. And good associations are the ones that are called Turing complete. So here on the left, I have a picture of Turing machine, and here on the right is a picture of a dynamical system, thinking that I'm taking the flow of a vector field. But I can also think of a dynamical system as a diffeomorphism, as a map, whatever. Here I think of a dynamical system as the flow of a vector field, okay? So I could make very strange associations between a Turing machine and a dynamical system. But the ones that are good are the ones which are called Turing complete, which are the ones we say that a vector field is Turing complete if it can simulate any Turing machine. And we have a way to test this, which may look very strange, which is the following. The halting of any Turing machine with a certain input is equivalent to a certain trajectory of the field entering a certain open set on the manifold. Okay? And here there are several definitions. Do you fix the open set a priori? Do you fix it a posteriori? There are different people working with different definitions, but here I'm going to assume that I fix the open set, okay? And I say that this association is good, so a vector field is Turing complete, okay? If the halting is equivalent, the halting of this machine is equivalent to the flow entering this certain open set, okay? And now we're going to see how this is connected to our poor rubber ducks, okay? Now imagine this poor rubber duck. Imagine that this duck, I'm able to associate to it a Turing machine in such a way that the trajectories of the duck are Turing complete. Now imagine that this neighborhood here, okay, is this open set is just a neighborhood of the Great Britain, okay? Then, if this association is Turing complete because the halting problem is undecidable, I'm not going to be able to decide if this rubber duck is going to reach Great Britain, okay? So that's a little bit the connection. It looks a little bit strange, and it takes a while to think about this concept. Now, because I need to talk about fluids, I need to talk a little bit about which definition of fluids I'm going to use. Because I want to talk, of course, about how to earn $1 million. Now we are getting serious. This would be to solve, well, $1 million nowadays doesn't look so impressive. But OK, still it's money, OK? So there is a list of collection of open problems still in the clay list. And still, as you know, only one of the problems has been solved. We'll get to that. And that's the Navier-Stokes problem. But the Navier-Stokes problem has, the poor cousin, which is the Euler equations. So the Euler equations are the equations that model the movement of the fluid, which is incompressible fluid, and inviscid. So it doesn't, I am assuming that it doesn't have viscosity. Of course, you think of water, but if you put some salt in the water, then you may have this viscosity. So maybe the model is not so good for the water of the sea. Okay, so we have here the classical equations, which we'll write like this. And indeed, what I want to say today is that these equations, which are classical, okay, the first one, this gives me what elements we have here. X is the velocity of the fluid. P is the pressure, okay? And, well, the velocity of the fluid depends on time, okay? So this first equation dictates how this evolution in time is occurring. What is very important here to know is that P and X, both of them, are unknowns. So the evolution of X also changes the pressure, okay? And then we have this second condition, that is that the divergence of the velocity is zero, which we can think of it geometrically as saying that the flow of this vector field preserves the volume. So indeed, we can also think of these equations in a geometrical manner, because here we have, we use the vector calculus standard language, but we can think of it as a covariant derivative. And indeed, these equations make sense. Okay, the classical equations are on R3, where the standard the metric is the Euclidean metric. But it would make sense to consider any metric. You say, okay, but if you change the metric, then you are changing the rules. You are no longer working on classical problems. Wait a minute, let me use the change of metric and see how I can use it. And it's going to be very important for me today to be able to change this metric. So well, if I change the metric, I can write the equations in a very similar manner. It just changed this expression here by the covariant derivative, where I just take the Levi-Civita connection associated to the metric G, okay? And the second equation is the divergence of X, which makes perfect sense. I can do this in dimension 3. Okay, I could do this in higher dimensions, but okay, today we can focus on dimension 3, if you want. So, indeed, as it happens, as I said, these equations are important because they look at the evolution depending on time. Okay, evolution depending on time. Okay? Now, I want to solve these equations. If you give these equations to a geometer, first thing, let's assume that these equations are as simple as possible. So let's assume that the velocity of the fluid doesn't depend on time. So what happens if the velocity of the fluid doesn't depend on time? That this term here is 0. Okay? So the equations that I get are of this sort. If you give these equations to a geometer, the geometer is going to play a weak game with them. Don't maybe leave your equations to a geometer, or maybe yes. You have a metric G. I told you, I'm going to use this metric. What you can do is to contract the metric G with the vector field X. What does this give you? A one form, okay? A one form. What is if this one form was contact, as the ones that were studied by Paulette-Lieberman? This would be amazing, right? We are working in this direction. Let's see. So alpha here, this alpha here is just the contraction of X with the metric G. And it turns out that if you work a little bit these equations, you can write them geometrically as in this way. This is an equation that I can look at saying that some form is exact in the language of forms. If I like, the RAM cohomology, I'm this kind of person, I like to know if a form is closed or exact, then these equations can be seen as a certain form is exact, a certain form is closed. Attention, I use mu here. Who is mu? Mu is a volume form, okay? And, well, by the way, this equation is exact, and the function that makes it exact is very special. It's the Bernoulli function, which, again, depends on the metric I'm using. It depends on the pressure, okay, plus 1/2 of the norm using the metric of X. Well, there is a class of vector fields, so this would be a solution, what we call a stationary solution, okay? Oh, it's not so interesting. Wait a minute. Sometimes, to consider critical points is important. So we can think of this stationary solution as some critical points. If you want to build up Moore's theory, you need this critical point. So these stationary solutions are important because they are some kind of critical point of some functional. And an example of solutions to these equations are Beltrami fields. Beltrami fields are vector fields which are parallel to its curl. Okay, and well, I need the condition that the divergence is 0. And examples of Beltrami fields are the Hopf fields on S3, okay? And the ABC fields on T3. The ABC fields are these fields here, where use A is Arnold, Beltrami, and Childress. They were important fields for KAM theory, okay? So these are examples of Beltrami fields, okay? And now, let's go to the $1 million problem. As I told you, well, mathematicians, we work, but we had a list of things to do. and we just solved one of the problems. We have this list of problems, and we just solved one of the problems. And as you know, the person who solved these problems didn't even pick up the prize. That's what makes us so interesting, maybe. So in this list, or strange, whatever you choose, in this list, I'm going to focus on the Navier-Stokes equation problem. And I'm going to try to see why Terence Tao was interested in Turing machines associated to a fluid. Okay? So, well, the Navier-Stokes problem, I'm going to do like Frederica, put a lot of pictures here. And, well, what we do is to perturb, so the equations, Navier-Stokes equations, are equations of incompressible but viscid fluid. So I have viscosity. And viscosity is here in the equations. And viscosity, in a way, it's what makes things interesting and complicated. I had a way to talk about geometrically to talk about the stationary solutions of the Euler equations, but we are not able to do this. We don't know how to do this. Maybe it's not possible in the Navier-Stokes case. And then, in a nutshell, the Navier-Stokes problem, what can give you $1 million, is the problem to determine whether for all initial conditions, okay, starting conditions of the fluid, you have smooth solutions that evolve indefinitely, or whether in certain circumstances solutions may lead to singularities, okay, may degenerate and blow up after a certain time. Is this natural? Think about it. What does it mean? It means that, like that, you could have a tsunami here. So that, if that is true, if one can find a counterexample of some initial conditions that blow up, this would mean that Navier-Stokes equations are not the right model, okay, to work with viscid fluids. So this means that one should change the models. So that would be an important consequence. So this explosion indeed corresponds to the singularities, region of a space where the energy of the fluid becomes concentrated to the point of being infinite. If you want to look at the exact formulation of the Navier-Stokes, okay, you can look at the clay problem, okay, and you can pick which problem you can solve. And then you see that Pfefferman gets very serious at what it means, because one can make some initial choices that lead to blow up, but these initial choices are very crazy. There are some conditions. If you go to the rules, what you need to do to gain the prize, you'll see, these are Navier-Stokes equations written in coordinates, and you'll see that you have some initial condition, but this initial condition is subject to some constraints, okay? We want it to have some constraints. The energy has to be bounded somehow, okay? And the partial derivatives have to be bounded. So we have some conditions. And indeed, Pfefferman formulates the problem on R3 and on the 3 torus. And the 3 torus is natural because it corresponds to symmetries, okay? So to the case in which you could have some symmetries. And indeed, he gives like 4 scenarios. I mean, you earn the $1 million if you can prove existence and the smoothness of Navier-Stokes solutions on R3 or T3. Here I chose the case of R3. Or the breakdown, okay? What has the expression breakdown of Navier-Stokes equation, people are talking about it as blow up, okay? So this connects us, well, indeed, connects us to the work of Olga Ladyzenskaya. Not many pictures of women mathematics today, so I'm adding some. And here, indeed, she was able to prove smoothness of the solutions in dimension 2. And she struggled to prove dimension 3. She wrote a book about this, but the 3-dimensional problem, as you know, is still open. And now let's go back to this question of Tao. Indeed, Tao proved the blow-up of some averaged version of the Navier-Stokes equation, and he did it using some dyadic models. And indeed, this was in a paper which was published at the Journal of the American Mathematical Society in 2016. And then he said, one could hope to design logic gates entirely out of an ideal fluid if these gates were sufficiently Turing complete, in the sense I described before, and also noise tolerant. Noise tolerant, it means that I can start to try to work with the Euler case, okay, and think of the viscosity as a perturbation, okay? One then could hope to combine enough of these gates together to program a self-replicating Von-Neumann machine. So in this paper, and later in other papers in 2019, we already see that Tao's dream was to create initial entry program to evolve as, so to create some initial conditions, which he was thinking of the Euler equations, okay, that you could plug in the Navier-Stokes equation and that they could generate this blow-up. And thinking that in order to have blow-up, we have to have this concentration of energy, his idea was that this initial condition had to be somehow Turing complete, because they had to have this idea of self-replication Von-Neumann machine, which, as I said, this is exactly a Turing machine. So that was conjectural, okay? And that was a dream that still didn't come true. But indeed, during the pandemics, well, indeed, this was before the pandemics. I was working with Daniel Peralta Salas and one of my PhD students, Robert Cardona, on a different problem, on this problem of finding a geometrical interpretation of fluids. And then when I was taking the train back to Barcelona, I was looking at Twitter, okay? And then in Twitter, he had asked a question which is related to this problem. The question was about universality of the Euler flow. And then I thought that we could try to use our techniques, which were geometrical, to attack this problem. And this is how we started to think about the problem. It's not that we were working on this problem. Of course, here I'm explaining the story in such a way that you can buy it, but we were working on a different thing. So to finish my talk, I'm going to present to you the construction of this fluid computer, and I'm going to try to explain what this does and what this doesn't do. Our fluid computer was able to reply to the dream of Stanislav Lem, but was not able to reply in a satisfactory way to the dream of Terence Tao. Okay? Though when we were working on this fluid computer, we could solve one of the conjectures that Terence Tao was asking. But I will not talk about that conjecture today because that had to do with the time-dependent situation. I'm going to talk about stationary situation. So the fluid computer, which this would be the picture of how I think of this fluid computer, okay? The idea to do this fluid computer is going to combine the construction that I explained of Moore, okay? So what's a fluid computer? A fluid computer has to be, indeed, a dynamical system that I can associate to my Euler flow, okay, in 3 dimensions. So the idea that the building block of this construction is going to be the construction of Ghrist-Moore. The construction of Ghrist-Moore is we associate a Turing machine to a mapping between two square counter sets. Okay, square counter set is 2-dimensional. The fluid computer I want to build is 3-dimensional. So I'm going to explain how I'm going to fill this gap using geometry. So that's the summary of where we are. The question is hydrodynamics capable of performing computation was posed by Moore in 91. These 29,000 rubber ducks were lost in 92. In 2007, a rubber duck showed up in Scotland. And in December 2020, right, in the middle of the pandemics, that was a good excuse to work home and use Zoom. We were able to construct this 3-dimensional Turing machine. And we're going to take this Turing, this fluid computer is an association of a Turing machine to a dynamical system, and this dynamical system is the stationary solution of an Euler flow. It's a Beltrami field, okay? That's what I'm going to do. And as a consequence, this will tell me that there exist fluid paths which are undecidable because of the halting problem is undecidable. This would be a corollary, an important corollary of this result. Okay, so if you want, apply it to the DAX. This will give me an interpretation, though I don't know if the DAX is going to follow exactly the path, my Beltrami field. If the DAX follow my Beltrami field, which is going to be interesting, then this would explain why you cannot find them. Okay, so that's a little bit the summary of what I'm going to explain. So our construction uses the idea of Ghrist-Moore, okay? And the idea of Ghrist-Moore is two-dimensional. I need to go to 3 dimensions. Okay, so I think of this two-dimensional construction of Ghrist-Moore, which is a mapping between 2 square Cantor sets, as a Poincare section of the vector field I want to construct. I want to construct a vector field in dimension 3. And I think of this dynamical system that Ghrist-Moore constructed as the Poincare section. Well, some of you is going to say, wait a minute, he just did define this mapping on the square Cantor set. Okay, I need to extend a little bit, I need to work a little bit harder, okay? So I need to extend the construction of Moore to a disk. So I have a diffeomorphy of a disk, which is volume preserving. And I want to find this three-dimensional situation in which the Poincare section gives me exactly this mapping. Now, I need to do a little bit of work in geometry, because the vector field that I need to have some special geometric features which we call Reeb vector field. And the Reeb vector field is associated to a contact structure. And now it's going to make sense, my obsession of trying to read the Beltrami equations geometrically using a smooth one form. So I need to talk about geometries of forms. And this is something that Lieberman did very well. And I wanted to show you this picture, but indeed I don't need to be symplectic today. Okay, let's forget about symplectic. I just need to define what is a contact structure. Indeed, I just need it in dimension 3. I can do it in any odd dimension, but I just need it in dimension 3. A contact structure is given by a one form, which satisfies the condition that when I wedge alpha, which is differential to alpha to n, this is a volume form. In the case of 3 dimensions, the condition is very simple. The condition is I wedge alpha, my one form, with the differential of alpha. Okay, alpha is a one form, the differential of alpha is a 2 form, alpha wedge the alpha is a 3 form. I say that this is a volume form on my manifold. That's the definition. And then what's a Reeb vector field? Well, once I have my one form, the Reeb vector field is given by these 2 formulas. First, it's possible to check from this condition that the differential of alpha has a one-dimensional kernel, and the Reeb vector field is in this one-dimensional kernel. But this one-dimensional kernel gives me one solution and all multiples of the solution. How do I choose one? I take one such that alpha of r equals 1. Once I have the Reeb vector fields, I can define Hamiltonian dynamics on these contact manifolds, but this I will not use today, Hamiltonian dynamics. It's for another talk. So an example of contact structure is you take the standard contact structure, which indeed Martinet proved that any contact structure can be written like this. Well, maybe it's back to Darboux, according to the book of Lieberman-Marlow. Okay, that I can always write locally a one form in this term. So how do I understand this condition of the volume form? I do this computation, and alpha wedge the alpha gives me the standard volume form. And how do I think of this condition that this is a volume form? If I look at the kernel of alpha, this gives me these 2 vector fields, okay? And this distribution is not integrable, because when I do the Lie bracket of this vector field with this vector field, quickly, where is Baptiste? Baptiste Coquino, you are there? Quickly, what is this computation? I know the list of... okay, you said partial of z. You are correct. Okay, when you do the Lie bracket of these 2 vector fields, you get partial of z. Okay, I looked at the list of all registered participants, so I could ask anyone here. Okay, and partial of z is not a combination of these. So, indeed, we don't have integrability. because this is not an integrable distribution. So the condition that alpha wedge the alpha is a volume form is equivalent to non-integrability of this kernel, which we can see in this nice picture by Robert Grice. This is a picture of the kernel at each point, and this kernel moves in all possible directions. So there is no surface such that the tangent space is this vector field. And now you're going to say to me, okay, yeah, that's cool. I want to go home and tell my family that contact structures are cool. Give me a good reason. You can also use contact structures to parallel park your car, okay? Indeed, well, we know, right, how easy it is to park your car. Just take 4 steps in science fiction. But indeed, it was a contact geometer, M.E. Murphy, who proved that indeed it's possible to parallel park. And the statement is, a car of length L can be parallel parked in any space of length L plus epsilon. This is what I'm going to tell to the guy in front of me when I don't park well. Epsilon sometimes goes to 0. Watch out. So that's an application of contact geometry. But OK, let's get serious. What I want to tell you today, just to finish my talk, I want to convince you that we saw Beltrami fields at some point. They were stationary solutions of the Euler equations. Now I'm talking about Reeb vector fields. I want to convince you that they are the same. Best way to convince you is to take an example. I take Hopf fields, okay? And I took 2 different presentations of Hopf fields. That's the S3. I take a 1 form, and I compute. I tell Baptiste, compute this quickly, and he does it very effectively. He's very good. And he computes the Reeb vector field, and you get this. That's exactly the Reeb vector field coincides with the Hopf field. A different presentation of the Hopf field is, you know, if you work with Daniel Peralta Salas, you learn that there exist Hopf coordinates, because he's a clever guy. And indeed, in Hopf coordinates, the Hopf field is indeed constant, has constant coefficient. So this allows you to check very quickly that it's a stationary solution of the Euler equations, that it's a Beltrami field, because when it's constant, then it's parallel to its curve. It's very simple. So indeed, this tells me that the same vector field can be seen at the same time as a Reeb vector field and Beltrami field. If this is true always, this is fantastic. So I just need to ask the experts in fluids. And here I have, Sullivan already had the idea that they had to be the same. But indeed, this was proved by Etnyre and Ghrist. Okay? They took back these equations that were written in some slides before. This is the language of, these are the stationary equations in the language of forms. Some form being exact, some form being closed. And indeed, from these equations, you can check that the statement is that if I give you a Beltrami field, this one form is going to be contact. Okay? And indeed, there is a one-to-one correspondence. This is fantastic. Maybe you don't get exactly the same vector field. Maybe you need to rescale. But the exact statement is that any non-vanishing Beltrami field with positive proportionality factor is a reparametrization of a Reeb flow for some contact form. And what's the relation? There is a kind of mirror, like in this picture, which is the picture of Lake Louise. Okay, far away. I could have taken a picture here. Well, never mind. So indeed, we have a perfect mirror. In one side, we have Beltrami fields and fluid dynamics. And on the other side, I have contact forms. And contact forms, when I vary the contact forms, on the other side of the mirror, what varies is the metric. The metric has been somehow silent, but metric is fundamental for me. Okay? So indeed, thanks to this magic mirror, there are many things we could do. And in the, I don't know, when they asked me, what will you talk about? I said, I will also talk about escape orbits. This is true. It's possible to apply this mirror to detect escape orbits. But then when I was preparing the slides, I said, Eva, you are not going to be able to explain all this. So I apologize. If you want to discuss about escape orbits and this application, I'm happy to do this somewhere, some other moment. But let's go back to the proof. And with this, I finish, because I went over time. Well, I started later, right? Now is when I start to ask for more time. but this is not good. Yeah, I'm going to finish. So let me finish the proof. Okay, I go from dimension 2 to 3 dimensions. In dimension 2, I said, I'm going to consider the mapping of Moore, have a square Cantor set. It's clear that I have a Turing machine, because I do this association with internal reform, and I get exactly Turing machine for each point of the square Cantor set. So I'm happy with this. And now I just want to look at this as the time one map of a Reeb flow. Okay? So what did we do? I said, it's possible to prove it, and it's very easy to prove it. We just need to apply the path method in contact geometry. But it's just, so what we did is to construct a flow, okay, such that such that the time one map gives me exactly this flow. And this is the flow of a Reeb vector field. So once I have the flow of the Reeb vector field, what do? I use the mirror. I said, hey, I have a Reeb vector field. On the other side of the mirror, there's going to be a Beltrami flow. And because it's Beltrami, it's going to be a solution to the Euler equation. And that's how you finish the proof. And that's exactly the fluid computer. Okay? So with this, we prove this theorem. I have done the proof, with except to the way I apply Moser's path method. But we prove that there exists an undecidable flow in S3 or in any compact manifold, okay, that is Turing complete. The metric that makes these stationary solutions of the Euler equation can be assumed to be the standard one, in the case of S3, the round metric, in the complement of where I'm doing some crazy changes that I use the mirror. When I use the mirror, if I perturb here slightly the contact form, which I have to do because I do the path method, on the other side, I'm going to change the metric. So the metric is going to change dramatically inside this solid torus, which is just the product of the disk with S1, okay? So, but I can now, because the whole thing problem is undecidable, and because this association is Turing complete, the corollary, and that's the important corollary, there exist undecidable fluid particle paths, so there is no algorithm to decide whether a trajectory will enter an open set or not in finite time. Now, just to finish, you're going to ask me, did you get $1 million? Of course not, otherwise I would be, on the news, maybe not. Well, the short answer is no. The long answer is read the paper, but let's say we took our construction, we plug it on the Navier-Stokes, and we were able to look at the evolution, and wait, the evolution is like that. So it exists for all time, so no blow up, and also because of the exponential decay, this just simulates a finite steps of a Turing machine, so the association is not good. So we cannot fulfill the dream of Terence Tao, but we can fulfill the dream of Stanislav Lem. And with this, the conclusions, okay, is that, well, for some systems, it's not possible to decide if practicals will enter an open set or not. And no matter how potent the computational problem is, the problem is not computable. And now going back to the idea of tau, if you perturb, can you think of the viscosity as a perturbation parameter? We found a theorem in computer science by Bournes, Grassa, and Henry that suggests that it's not possible to construct Turing-complete systems which are robust by perturbation. So it seems that we cannot get this counterexample just by perturbation of the Euler equations. The way to get it should be much more complicated. So thank you very much for your attention.
Thank you, Eva. As we are late due to my fault, not your fault, sorry.
We all will.
Yes, so I think, Eva, you will be there during the 3 days, so yes. You will have time to ask questions. Perhaps one question to Eva, one smart question.
I don't know whether it is smart, but I would like to understand which of the mathematical feature of a Cantor square makes it interesting for object for you. Maybe some ultramatrix structure. Or?
Yeah, that's interesting. That's a very smart question. Yeah, so we could, and that's a very good question. I mean, you could try to take another fractal, okay, and see if you can associate a Turing machine. I mean. The thing is that there is some work done by some people in computer science in this direction, but we still didn't see if we will, because our construction is the machine that we associate is universal. This means that the other construction is going to be equivalent. So we didn't try, but there are some, there are some works. So fractal is the key word. That's what makes it special, because you want to have this kind of logical chaos. And in a way, that's where you get it. That's the short answer. And then, I mean, maybe I can advertise some crazy new idea that we are working on, which is to relate this construction to topological. Well, it's a bit too early, but we are able to, in a way, to construct some new extension of fluid computers at Feynman, and we use topological quantum field theory for that. But we are still maybe not ready to, this is not written, but I want to advertise this. We are working on this kind of ideas. But this idea of the fractals, it's interesting too. We're still not working on it.
Okay, so thank you, Eva.